Before we jump into an example, I'd like to mention about the difference between knowing the sigma and not knowing our sigma values. So when we know sigma, which again is the symbol used for population standard deviation, when that is known quantity or an assumed quantity, then our formulas and our calculations are going to revolve around the normal distribution using z-scores and the critical values called z sub c. On the other hand, if the population standard deviation is unknown, that means that we're going to be using the sample standard deviation denoted S. That's going to be a known quantity that we're going to use. In cases like that, we're going to use the t distribution instead, along with the critical values denoted T sub c. So if you look at the formulas, you'll see the different versions of formulas with either the z or the t, and the big defining characteristic that differentiates the two is whether or not we're using the population standard deviation or the sample standard deviation. And here are the formulas that will be provided with the exam. Notice again there are two different versions for confidence intervals, either sigma known or sigma unknown. And when sigma population standard deviation is known, that's when we're using the z and z sub c versus the other formula which has t and t sub c. We're going to work through this example here. It says the breaking strength of cables produced by a certain manufacturer have a population standard deviation of 102 pounds. A random sample of 80 newly manufactured cables has a mean breaking strength of 1,950 pounds. Based on this sample, find a 90% confidence interval for the true mean breaking strength of all cables produced by this manufacturer. Okay, a key thing here is, again, population standard deviation. That's our value for sigma, 102. So since we know the population standard deviation, we're going to use the margin of error formula that goes E is equal to Z sub C times sigma over the square root of n. And we know the value of n, that's the sample size. Sample size here is equal to 80. We need to know the value of the critical number, or the critical value for z, given by the z sub c. That we look up in the table. Here's our table, and we pick out the value based off of our confidence interval, and they give us a 90% confidence interval or confidence level, which means we're going to use the 0.9 here. So our critical score for z sub c, or the critical value, is 1.645. So we're going to plug that all in to our formula here. We'll get 1.645 times 102 divided by the square root of 80. And we'll round that off to the nearest tenth to get 18.8 for the margin of error. Now to get the confidence interval, what we're going to do is we're going to take the sample mean, subtract the margin of error, take the sample mean, add the margin of error. Our sample mean quoted up above, if we look back up, their mean breaking strength of 1,950. So that's going to be the number we would use with the margin of error here. We'll do 1,950 minus 18.8 and 1,950 plus 18.8. That's going to give us values of 1931.8 and 1968.8. So that's like the lower number of the confidence interval and the upper number of the confidence interval. And sometimes we can write that as 1931.8 less than the population mean mu, less than 1968.8. On this one, it says executives of a supermarket chain are interested in the amount of time that customers spend in the stores during shopping trips. They hire a statistical consultant and ask to determine the mean shopping time, mu, of all customers of the supermarket. So they'll go ahead and collect a random sample of shopping times at the supermarket and use the mean of these shopping times to estimate mu. Assuming that the standard deviation of the population of shopping times is 28 minutes, what is the minimum sample size that must be collected in order to be 95% confident that the estimate is within 6 minutes of the population mean mu? Okay, so let's go through what we have here. Big thing here is, again, standard deviation is given, and we're assuming for the population here. So that means we'll be using the formulas accordingly. We want to know, again, the sample size. So the sample size formula for our population mean mu goes n equals parentheses z sub c sigma all over e, this in parentheses, raised to the second power. So we're going to need to, like before, find the value for the z sub c critical number. So let's write down our numbers we have here. We know sigma, population standard deviation, is 28. The sample size, or I should say the margin of error they'd like to estimate here, is 6 for 6 minutes. That's E. And then if we look up the value for Z sub C in the table, we're dealing with a 95% confidence interval. So here's our value for Z sub C, 1.96. So we just need to plug this all in the formula. N is equal to 1.96 times 28 all over 6. It's all in parentheses, raised to the second power. This is all approximately rounded up to 84. So that's the sample size needed in order to hit that particular margin of error with the given conditions here. This one says, consider a distribution with 28 degrees of freedom. Find the value of C such that P of T greater than or equal to C is equal to 0.10. So this means probability that T is greater than or equal to C is equal to 0.10. Now this T letter refers to the T distribution. So we have a table that goes along with that we're going to need to look up the values here. So here's our T distribution table. We have a few things we have to look up in here. We call it degrees of freedom. And there are these other values with decimal values that say like 1 tail, 2 tail, and level of confidence. So if we go through the table under the conditions that were given with the degrees of freedom, which is abbreviated DF in this case, and then we look up for this value that's given here, 0.10, we're going to look that up under the 1 tail column, mainly because it's just strictly greater than, so it's pointing toward one direction, and that means one side of the T distribution, one tail of the T distribution. So if we look that up here for 0.10, we get the value of 1.313. So our answer here is that the value of C is equal to 1.313. So what we can say is that the probability that the T would be greater than or equal to 1.313 is equal to 0.10. It's kind of like our z-score table. It refers to part of the curve underneath the distribution. That's why on the table they give you this little picture here where it shows different parts of the curve highlighted. And since we're dealing with T on the greater than or equal to side, that's pointing off to on the one tail side. Sometimes they call this also right-tailed. This one says, suppose a random sample of 18 adults has a mean score of 72 on a standard personality test with a sample standard deviation of 8. If we assume that the scores in the test are normally distributed, find the margin of error and the 99% confidence interval for the mean score of all takers of this test. The key word to highlight here is sample standard deviation. We are not given the population standard deviation, and as a result, we're going to need to use the different formula for margin of error that uses the t-distribution. It looks very similar to the other one. It goes E is equal to T sub C times the S over the square root of N. So our values for S is the sample standard deviation of 8. N is our sample size of 18. The number that we need is the critical value T sub C. Since we're using a t-distribution, we also need to know the degrees of freedom. Now, I didn't mention that in the last example. The degrees of freedom, it's also in the formulas, is equal to n minus 1, or the sample size minus 1. So that'd be 18 minus 1. So degrees of freedom is 17. So going through the t-distribution table to find the degrees of freedom here, if we go down there, we'll find that for degrees of freedom 17, we're also looking for the 99% confidence interval. So that means 0.99 under level of confidence. So there's going to be where we'll find our value for the critical value for T sub C, 2.898. So when we plug this in the formula, it'll look like 2.898 times 8 divided by the square root of 18. That gives us a margin of error of approximately 5.5. So for the confidence interval, we'll take the sample mean of 72, and we're going to add the margin of error and subtract the margin of error to that sample mean. So 72 minus 5.5, 72 plus 5.5. That'll give us 66.5 and 77.5. So the lower number and the upper number for the confidence interval, and we could write that as 66.5 less than mu less than 77.5. On this one, it says in a random sample of 275 students at a university, 228 stated that they were non-smokers. Based on this sample, compute the margin of error in the 95% confidence interval for the proportion of all students at the university who were non-smokers. Okay, this is a different setup than the last one and the last few examples, mainly because we're not dealing with the mean, we're dealing with the proportion. So if we look up in the formulas, there's one specifically for margin of error for population proportions. And this formula goes E equals Z sub C square root P hat Q hat all over N. So we need to talk about what each of these things stand for. First off, P hat is what they refer to as the population, or I should say, sorry, the sample proportion. And we don't have the value of the sample proportion immediately given to us. We have to get it by taking the ratio, the fraction of the numbers that are given. So out of the total sample of 275, 228 responded. And the answer to the question here stated that they were non-smokers specifically here. So if we take 228 divided by 275, we're going to get the sample proportion of respondents for that particular question. So when we divide to a decimal here, we're going to round it to 2 decimal places and get 0.83 for our sample proportion. Another component of this formula is this thing called Q hat. We calculate that by doing 1 minus P hat, or in other words, 1 minus 0.83. That comes out to be 0.17. And our sample size is 275, so that's the number for N. So all that's going to go in the margin of error, along with, again, the value of Z sub C. We actually found this one in a previous example, so you may want to check my earlier video where I found that. For the 95% confidence interval in the table, it's 1.96. So when we put that all together in the margin of error formula, E is equal to 1.96 times the square root of 0.83 times 0.17 all over 275. This comes about to be approximately rounded to 0.04 for margin of error. We're going to take our sample proportion, p hat, we're going to subtract the margin of error and add the margin of error. So 0.83 minus 0.04 and 0.83 plus 0.04. That'll give us numbers of 0.79 and 0.87 for the lower number and the larger number in the confidence interval. So that allows us to say that the confidence interval could be stated as 0.79 less than mu less than 0.87.